Welcome everyone, lecture 3. So we spoke about logistics assignment 1. There is also this paper presentation slot. Maybe we should share this on the page.
Google Sheet that has a bunch of papers, I think around 70 papers listed with all links and different topics. So the plan is that every lecture we have 3 presentations, and every paper has 2 presenters, so we'll have 6 presenters for every lecture. So please just select a date and form teams and write both the presenter's name in the columns E and F. Also, we're going to have 3 total presentations per day. So right now I see February 18th has 4 people signed up on it, as you can see in column H. So if you see something that has 3 slots already filled out, make sure that you don't leave that in. And yeah, some of these papers are pretty difficult and maybe in-depth. So how long are the presentations?
3 minutes.
3 minutes?
3 minutes.
Yeah, so 3 minutes. So if there's a lot of theory, maybe don't focus on that and just focus on the high-level takeaways. A lot of them will have a ton of experimental details, all of which may not be necessary. So focus mainly on the methodology and what problem is trying to solve. Just keep it high level, and we will ask questions for more details if necessary.
I think we'll probably share some guidelines around it.
Yes.
On Discord. Note that because we've done this presentation before and they can always run over, so we'll actually have you record your presentation ahead of class. So we're not going to do it live. We'll record it ahead of class. You submit the recording. We'll actually play the recording in class, and we'll have you stand here and answer questions. Okay? So that we are going to keep time, because the class time is being used for this. We don't want to run over. So it'll be the last 15 minutes of class starting next week. So every week, the last 15 minutes will be 3 presentations, at most 3. So like Arnav said, make sure to check the last column and see that there's no day. Like if you're picking February 18th, it's already full, right? So pick a different day. Okay. So if you have a preference for a day, then pick it right now. Like later on, you may not get your preference. Okay. So it's important to, if you think you have a constraint or a preference, then work with what's available today. If you pick 3 days later and you say, I want this date, sorry, it's not available. You'll have to work with what's available. Okay? That sound good? Yeah, and so again, don't use ChatGPT to summarize or use your presentations. The reason is you'll be graded on your question answer part. So after you present, we'll ask you questions. So if you use ChatGPT and you're like, oh, I don't know, it's all in the presentation, then you're not going to get the grade. I'm sorry. So make sure you actually understand the paper, and then you make the slides based on that. Okay? Or even if you use ChatGPT, make sure you know how you can answer the questions. Okay? Or really understand what's being there in the paper so you can actually answer questions. The questions will be well thought of as well for every paper. So we'll actually look at the paper ahead of time, and we'll come up with some questions. Yeah.
Are we submitting on Canvas the recording?
I think the recording details we'll set it up. I think there'll be a drive probably, so you can submit to a drive, a Google Drive, and then so we can just play it from that drive. Okay, so we'll have it formatted by date, so we know which day, which presentation. We'll just go by that. Okay, any other questions on this? So this is very important. It's a very important skill to be able to read a paper, understand it, distill it, and summarize it in 3 minutes. You only have 3 minutes. So you'll have to pick and choose what you want to present and record it ahead of time. And you may actually have to do more than one recording to get it right. Okay, so just make sure you do that homework, and then it'll be great. So once you have that polished presentation, it'll be a lot of learning for everyone. So we can share the learning through your presentations. Okay. So all of these papers, I think, are in the past 2 years, 2-3 years. Yeah.
Max 4. But
Yeah, at most 4. So they're very fresh, and they, like, Arnav's done a good job of categorizing it by topics. So there's so many different topics that it covers, and some of these topics we're not going to cover in the course, so that's perfect. So we don't have to cover things that are already here. So it's going to complement the class learning as well. Okay. All right. So going back, that's on paper presentation. So then we have assignment 2, which is coming up, will be assigned probably tomorrow and then due next Tuesday or Wednesday. So we have 2 assignments and 3 mini projects, right? So we're going to have the second assignment assigned tomorrow. It's going to be on, it's going to be again on classification, but you're going to be able to try out ChatGPT Nano and BERT. So you'll be able to fine tune a BERT model, and you can use ChatGPT Nano out of the box. You can compare and see which one performs better. So that's assignment 2. So you'll get to work with the API for GPT-4 Nano, and you actually fine tune a BERT model for the other scenario. Okay, so it should be good hands-on experience, and very practical, because while we talk about GPTs and LLMs a lot, we still use BERT for production use cases in the industry. So that's going to be a nice contrast for you with assignment 2. So that's assignment 2. Anything else? Any other questions, call outs about the course or anything? Okay. Okay, so last lecture we went through the history of large language models, and we also looked at LLM use cases in the industry. And we also had a group discussion. We formed groups and people spoke about some pet projects and industry use cases that they would like to brainstorm on, and hopefully that was a good exercise for you guys. So today's lecture, we're going to cover deep learning fundamentals. So it's going to be a lot of material, and we're going to be like going a little bit fast, but hopefully this is something that you've seen before in a previous class, so it's not completely new for you, but it's going to be a refresher. And we'll also have some in-class exercise. So one thing I want to say is that we're going to have 5 in-class exercises today, and we're going to submit it on Canvas. So maybe just log in on Canvas and have the in-class exercise ready, so you can actually submit. It's a multiple choice, so you just submit a multiple choice. As we go through the in-class exercise, you just submit your choice, and then when you're done with the class, you just submit the assignment. So it's very easy. It's very little work, but it'll test your concepts. So the in-class exercises are designed to test your concepts. So just make sure your setup is ready with the Canvas, and then I think the assignment, the in-class is ready, right, on Canvas?
I think so, yeah.
Yeah, okay, it's ready. So our grader, Hofe, set it up. So thanks to Hofe. Hofe is here? Hofe is not here. So he set it up. So, okay, so outline for lecture today is we'll go through motivation for deep learning, some DL applications, history, we'll go through logistic regression, one of the first and the simplest machine learning classifiers, a linear classifier, deep learning models, activation functions, and we'll do hopefully we have time for a small demo, TensorFlow demo, and then we'll look at training and backpropagation concepts, and then overfitting and hyperparameters. So kind of a gist of like a very quick rundown of classical deep learning concepts. Like if there's a nice reference for this. I think I don't know if the reference is here, but yeah. So the reference for this would be yeah, it's here. So this one, Bengio et al. If you click on this link, it's really good. So each of these might be a separate chapter in that book. We're just compressing it to one lecture. Okay, so we're going really fast through this. Okay. Okay. So introduction to deep learning. there's been a lot of buzz around deep learning in the past decade and a half. Before LLMs became popular, deep learning was the big deal. And deep learning kind of led to LLMs with transformers, right? So deep learning refers to neural networks. That's a loose approximation of how the brain works. We spoke about this last lecture as well. And traditionally, deep learning has been used for a wide variety of applications, both in language, in vision, in anomaly detection, and many other places for monetization, marketing. There's many different places you can actually use it. So self-driving cars, that's kind of computer vision, sentiment analysis, text summarization, arrhythmia detection, so anomaly detection. Yeah, we used to have this as an assignment for a course, but probably not this one. And then, so this is a health use case. Image to text generation. I think we'll touch upon this in this course. Yes, image to text or text to image. We'll do the reverse. So with and then machine translation. This is still pretty popular. And actually, it's gone to the next level with voice translation and accent translation. So machine translation was a big deal 10 years back, but it's kind of a solved problem. Like models are very accurate, but now we have voice and accent translation. You can speak in a certain accent or a language, and then the receiver will receive it in a different accent and different language. So it's pretty cool. So everyone's happy with their language and their accent, right? So autocomplete, like you use Gmail, then you have autocomplete, and that's a very traditional application of deep learning. Okay. And then more recently, we have chatbots that actually extend deep learning through language models and transformers. As an example of autocomplete, most of us have seen this. Image to text. There's some popular models, I think, Inception, V2, and other vision models that are based on some deep learning architectures that can look at an image and transcribe it with a text. Of course, LLMs can also do it, but these models can be faster. They can be much faster. Arrhythmia detection, I think we mentioned earlier. This is a very interesting, if you're into anomaly or fraud detection, or there's like different kinds of anomalies. There's like point anomalies. Like these are point anomalies because they stand out, right? Like you look at it and say, oh, it stands out. Whatever stands out in a very obvious way, that's a point anomaly. And then you have like more of a segment anomaly. Like in this case, like I think this is a segment anomaly. So because everything else looks different, like if you look at these segments, they look of one kind, but then this one looks different. So it's not that it's a point anomaly. None of the individual data points have any anomalous behavior, but when you look at it as a segment over a period of time, it looks weird. So this is a very actual use case where people who have arrhythmia or irrhythm, so the rhythm of the heartbeat is off. Or if you, I mean, this can even happen because of stress or whatever, is you suddenly feel your heart is pounding more than it should, or you can hear your own heartbeat. That's kind of connected to arrhythmia. So detecting this through smart devices requires more sophisticated deep learning based approach or segment based approach to anomaly detection, right? A very simple detection will not be able to capture this. So that's why you need deep learning to understand anomalies of this nature. Okay, I also put in some more industry-focused applications with a focus on NLP, actually. So tagging products at e-commerce companies with tags or category IDs. So catalog management, category management, category updates, categorizing your products. Like e-commerce companies have like thousands of categories and tens of thousands of subcategories, and a new category keeps popping up every day. Managing them, organizing them so that it's easy for customers to browse through is kind of a part of this, right? Coming up with category names. So some of the e-commerce websites have a lot of sellers, and the sellers want to list their items, and then they don't know which category to tag it with, or what would be like, should they create a new category because they have a niche product. So having recommendations and AI that can recommend category names could be like a example here. Summarizing reviews for products. I think we spoke about this on the first lecture. If you have too many reviews or lots of stuff going on, and I just want to get a gist of it, then this is a good application as well. Customer service help. We see a lot of this coming up with different travel companies, or even if you want to order food or wherever you can have a chat. Chatbots are becoming more and more ubiquitous. Some of them are good, some of them are getting better, and some of them are they really understand what you're asking for. Some of them need more prompting or limited usage, right? So developing good chatbots, that's another application. Live speech translation, we spoke about this. Speech, accent, and language translation. Again, it's kind of connected to customer support, but more nuanced. It's more sophisticated. Intent recognition, this is like a very fundamental task, you can say, because whatever language comes up, whatever you write or you say or you speak or you chat, you first want to understand the intent. What is being conveyed here? So intent recognition is very important. And connected to that is detecting malicious intent and content in text. So a lot of companies have moderation teams, like content moderation teams, that are mainly looking to moderate content and make sure there's no malicious, like anyone can type anything malicious and you're storing it in your database. So you have to have a filter before it gets stored, because you don't want to store anything malicious, and you don't want to query something that's already sitting in your database that's malicious and then deliver it. So that whole pipeline of data management layer should have a content moderation layer as well, so that you're not ingesting anything that's malicious, and you're not transforming it into something that's malicious. Even if you didn't ingest, your ingestion is fine. Have you guys heard of ETL pipelines and ELT pipelines? So you might ingest something, you might extract something, that's fine, but you transform it using LLMs, and that might introduce something that can lead to any malicious hint of it. And then you store it again, and then you load it. So you have to make sure moderation is there at every single step that uses sophisticated AI or data that might be coming from AI. So content moderation. And this one is, I think, this was quite popular earlier when it came out. People were like really surprised by it. But if you type in a natural language, hey, give me the top 10 products in this company that is generating revenue that's really good in this region in the last 2 years in this category. Okay, so you have a lot of like specifications and constraints. Convert that into a SQL query automatically, extract the results, and return it back in natural language, the same language that you asked the question in, right? So then you have, I mean, again, this is very novel earlier, but now I think it's you can still have mistakes and hallucinations here, but converting a natural language into a structured query language, getting the result, and then generate it back, right? And many more. So there can be many more applications in the industry. So Yeah. Cool. So a brief history of deep learning, uh, neural networks, LLMs, you can also say. A little bit more. We looked at some history last time, but this is by chronology. We'll go through. One of the first deep learning models came out in 1965 by Eva Keno et al. It didn't use backpropagation for training, but used something else called sequential least squares fit, a different algorithm. And the earliest convolutional neural network was by Fukushima et al. In 1979. Earliest backpropagation was 1985 by Geoffrey Hinton. He's one of the founding fathers of deep learning, along with Ian Goodfellow and Jan LeCun. And speaking of Jan LeCun, Jan LeCun recognized that you can actually do backprop for recognizing MNIST, handwritten digits, at Bell Labs. So he said, okay, you can do backpropagation, but where do I apply it? Let me try applying it to recognizing digits in images. So one of the first image recognition software, you can say, came through here. And then MNIST became a very standard data set. So for almost 2 decades, people were just like, I have a new algorithm that does better on MNIST. And only in 2010 that we had even better data with ImageNet and stuff. But something that, someone worked on in 1989 was still used till early 2000. And then LayNet was a big contribution by Jan LeCun, of course, based on his own name. And this was the beginning of XNets. So after that, there was like AlexNet, this net, that net. So people came up with different variations of neural network architectures and deep learning architectures, like Inception and so on and so forth. So this was like one of the first ones for by Jan LeCun. And then there was a discovery of recurrent neural nets, RNNs and LSTMs in 1997. So this there was like a lot of advance in the machine learning side and the architecture side, but there wasn't sufficient advance on the compute and GPUs and memory to match the implementation. So you had the theory in place, you had the concepts, you had the architectures, you had the prototypes, but you couldn't scale it. You simply couldn't scale it because there was not enough resources. So between 1997 and 2006, GPUs got faster, like 1000x computational improvement, right? So they got really, really fast. So that's when around this time people started going back to neural nets and saying, can we redo the implementation, see if we can actually make it practical? Can we make deep learning practical? Because until this point, it was still not considered practical. So 2011, Sirasan et al. Showed that you can train a CNN without pre-trained weights, just with good computational power. So it used to be that you had to pre-train the weights, you had to set up the weights to begin with, and then you train it. There's a whole setup that used to happen with neural nets. And in 2011, he showed that don't worry about setup, just throw data at the network, and it'll take care of the setup, it'll take care of the training, it'll give you good outputs. So we got done with preloading or giving priors to models so that it can do well, right? Because the model itself became very powerful that it said, don't worry about initialization. I can just work with the data and I can do a lot of training to actually understand and then generate good model weights. And 2012 was when the ILSVRC competition for ImageNet started to take off in the image and computer vision space. And models based on deep learning were beating all standard models for computer vision. Like people didn't believe the results. They said, this is not happening. Because there were computer vision experts who were like, no, we've been working on this for the last 10 years and you come and tell us that you have a new model that beats our benchmarks. That doesn't make sense. But then, paper after paper got published, and then suddenly it became clear that you have to go through the deep learning route. Because if you try to feature engineer, so feature engineering was more popular before deep learning, is you try to engineer features, just like you play around with objects or Legos, you play around with data and build data features, and then construct a final model. So that was like a two-step, three-step approach. And then deep learning came and said, don't worry about the two-step, three-step approach. Just throw the data at the deep learning model and it'll do well. So no need to work on the Legos. Deep learning will do it for you. So deep learning is also doing feature engineering, but it was automated. Before, we used to have manual feature engineering. You had to construct certain combinations of pixels, or you do some convolutions and extract features. Now deep learning would do it for you, right? So this is where we started to go from manual feature engineering to automated feature engineering. And then, so this was computer vision, and then a few years later, transformers arrived on the scene, and then NLP took off. So computer vision took off in 2012 with the ILS VRC competition, the ImageNet dataset. 2017, transformers started to take off. Transformers came to the scene. They actually started to take off, a little bit later, because people are still using LSTMs. It took some time, it took a few years, but then after that, it just took off. And definitely with ChatGPT, it really took off. Like after that, transformers became like a very popular word, right? 2020, the transformer got applied to vision. So with vision, CNN was more popular. It's still used, but then people didn't think that you could apply something in language to a vision model, because CNN was like bread and butter for vision, convolution neural nets, and then transformers became the go-to model for language. But could you take a language-based architecture and apply it to vision and see some gains? So they could actually match performance and said, well, we can actually match the performance. So if you're using transformers here, might as well use transformers there. It can also help with multimodal architectures, because now both are transformers, even the language and the vision component is transformers, so you can tie them together. So it gives you more flexibility if you can use transform models for vision as well, and not just language. Okay. So that was 2020. 2022, ChatGPT came on the scene, and then people started, it kind of became unreal with 3.5. Like, it was still hallucinating, but it was unreal that it could make sense, and it could actually construct sentences that looked reasonably polished, like without too much of hallucinations. It was a little bit of a shock that an AI could actually do it. If you remember that moment, like, oh, it's actually doing this? Is it real? Is someone sitting behind and typing this, or it's actually happening, right? So, and then, after ChatGPT took off, some of the big tech companies said, well, we also need to innovate, not just one company. So Meta came up with Llama 2 and released the weights in 7 billion, 13 billion, 70 billion. And it saw very wide adoption as an open source alternative to ChatGPT. Because until GPT-2, you could see what the structure was, what the architecture was. With GPT-3, 3.5, and so on, you had no idea what the architecture is, because the weights were kept private. OpenAI didn't release it. It became proprietary, right? So Llama 2 became the alternative for other companies who wanted to build off these advances. So they came up with a 7 billion, 13 billion, and 70 billion version. And they had a context length of 4,096 tokens. So you'll see these this terminology come in. So context length is how many tokens can you feed in the input, right? So there's the input token upper limit. So it was 4,096 tokens in 2023. And 2024, Llama 3 was released with 8 billion, 70 billion, and 450 billion parameters. So this was a big jump from here. And the context length limit was 8192 tokens. So you kind of doubled it up. And context length is important because let's say I have a lot of documents to feed in to an LLM. After a point, you're limited by the number of tokens you can feed in. You hit 8192 tokens, you cannot feed in anymore, right? So increasing context length was also important as these models evolved. So Llama 3, and I think other models also said that, well, we support 8192 tokens, but we can extend it to 128K tokens. So what that means is you can feed in 128K tokens if you want, but don't expect the performance of 8192 tokens. So it's possible, it's feasible, but you may not want to rely on it or bank on it. It's just an option, it's there. We try to extend the limit. So this is, Llama 3 is one of the most popular and performant meta model and also an open model so far. Unfortunately, the successor didn't do as well. And then DeepSeek did its own thing. Like last year, DeepSeek released their models with low budget and architecture additions like multi-latent attention and mixture of experts. And this shook up the industry because they were claiming similar performance to top models like GPT and Gemini, but with much lower cost. And so the companies were like, big tech companies were like, what are we doing? Why are we spending so much money if these guys are able to do it with less, right? So that really, these were disruptions. So the DeepSeek really disrupted the big tech industry, and that's good because it forces you to innovate. So it changed the path of Google and Gemini, and they're like, oh, we need to actually go back to our drawing board and see how we need to innovate better. Even though we are a big tech company, we cannot be lagging behind these kind of disruptions, right? And 2026, I think we spoke about it. There is more of a quest for superintelligence beyond just LLMs, with a focus on multimodal architectures and exploring multimodal reasoning and mimicking better how the human brains work. So the companies like Thinking Machines, which is Mira Murati spinning off from OpenAI, and AMI, Jan LeCun spinning off from Meta are a couple of examples. So again, we had a disruption early this year, 2026. Again, DeepSeek came out with a paper that doesn't just train existing transformers on better data, but actually it kind of changes the architecture, right? And they introduced something called MHC, manifold hyperconnections, extension of residual connections, which does better. So this is definitely another disruptive paper. So these disruptions are good because it forces people to innovate and inspires others to do better. So that's kind of a brief history of deep learning and LLMs. Any thoughts or questions? Okay, so we'll having gone through the history, we'll go back to basics. We'll actually look at some. We'll go back to the beginning, right? So with perceptron, let's look at a perceptron, and connected to that is logistic regression. So logistic regression is very much like a baby of deep learning, and deep learning is a much bigger extension of logistic regression, right? So logistic regression is linear and deep learning is nonlinear. So that's one, but there is actually more. So let's work through the nitty-gritties of logistic regression and the neural network model. So the idea of perceptron, which we spoke about last time, is like a single neuron, is the idea of differentiating, like the practical applications to differentiate positives from negatives through a linearly separable layer, right? So if you have linear separability, if data points like the positives and negatives can be separated by a line, that's like the simplest way to differentiate two classes, and logistic regression applies in that case. So it's nothing fancy, it's nothing complicated. A simple line will help you separate two classes. You just have to identify the line. You don't know if this is the line. You don't know if this is the line, but actually this is the line, right? Oops, sorry. Okay. So this is this. It's actually this line, right? So anything between these two classes will do the trick, right? So linear separability is like the simplest assumption you can make in classifying data points into positive class or a negative class, because you can have more complex separations. You can have nonlinear separability, and that's where the next level of logistic regression or deep learning models come in. Okay. So perceptron is like the precursor to logistic regression. And perceptron is a mimic, it mimics a single neuron, right? So the idea is like you have an entry point here with different weights for the different input indices that are coming in. So let's say a vector x, this is the input, but the input has d dimensions. So you say x is in Rd. So if we lay it out, you have like a constant here, intercept, and then you have the d dimensions of the input. So x1 through xt. So you can think of x as x1, x2, xt. Right? So it lives in d dimensions. So we have d dimensional input, and corresponding to these inputs, you also have d dimensional weights, w1 through wd. And these weights are computed ahead of time, right? Or they're trained. These weights are trained by data. So you have an input here, and then you have weights here, and then you have linear transformation here. And then the linear transformation is basically a dot product between the weight vector and the input, right? So the weights interact with the input in a linear way, the simplest way you can interact with input. And then whatever you get as the outcome of this, you pass it through a nonlinear step function. If it's above 0, you say it's a positive class. If it's below 0, it's a negative class. It's very simple. So that's a step function. And then you predict +1 or -1. So that's how you go from something that's quantitative, floating point vectors, transform it through the weight vector, and make it go through the step function, and then generate +1 or -1. So that's how if you show an image, again, vectorize it into some dimensions, pass it through this, and then at the end you get a cat or a dog. So how do you go from data to cat or a dog? This is kind of one model, a simple model of transforming the numerical or quantitative representation of the data through weight matrices, right? So the thing with logistic regression is instead of the step function, you have a sigmoid. But that's the difference. Just replace the step function with a sigmoid and you go from perceptron to logistic regression. Okay. A simple example of a perceptron is like the OR function. So what's the OR function look like? So if you have x1, x2, sorry, actually, so this is x1, sorry, is x1 and x2. So you have either 0, 1 and 1, 0. So when is OR, when is it true? When x1 is 0 and x2 is 1. So it's true here. Is it true here? Yes. Is it true here? Yes. Is it true here? No. Okay. Can I draw a line to separate the green from the red? Yes. So maybe I can draw a line like this. Yeah. Maybe I can also draw it, sorry about that. Okay, maybe I can also draw it this way. So there's more than one line that can separate the red from the green, right? So if I had many such data points, I can make that a x, and my x is now in 2 dimensions. Remember we said x is in Rd. So here's an x that's in 2 dimensions. Learn a weight vector. What's a weight vector being learned? It's actually this dimension. This is what the w is. So for any line the vector perpendicular to that is the weight vector. So learn a weight vector through whatever, optimization or loss function optimization or training, so that you can separate the red from the green. So the simplest example of binary classification. And the same goes for and. And is the opposite of or. So the red and green are reversed, right? Still the same. You can still learn linearly separable. So the key thing is you can learn a linearly separable function to separate the green from the red. Okay. So now let's look at a different example. XOR. I just want to give a contrast. So XOR, we have x1, x2, we have 0, 1, and then 0, 1. So when is XOR green? At 0? Here, right? And then at 1, it's at 0. And here, it's not true. Yeah. Is there a line that you can learn to separate the red from the green? Yeah. How about this? No. How about this? No. So you simply cannot have a line separate the red from the green. So the problem is more complex. So logistic regression would fail in this scenario, right? So with just 2-dimensional data points and with just 4 data points, we show how things can get so super complex very quickly, right? So this is where logistic regression fails. Because there's no way you can linearly separate plus from minus. Yeah. So there's no way you can separate the x from the check. Yeah. Okay. So going back to logistic regression, so we said that we replace the step function with the sigmoid, right? The sigmoid is like a S-shaped function, and it is 0 if it's close to 0 if it's very negative, and it's close to 1 if it's very positive. But practically it doesn't have to be very large for it to be close to 1 or negative 1, because it's like an S function. Very quickly it starts to hit a 1. And it's represented by this, right? So the sigmoid is 1 over 1 plus e to the negative score, whatever that score. And the score actually comes from W transpose X. So you take the W transpose X that we saw previously and put it in here and pass it through the sigmoid, and you get something between 0 and 1. So sigmoid also changes whatever is input into it into a probability, or it changes it into a 0, 1, which is something between 0 and 1, right? Okay. So logistic regression, like we said, it uses a sigmoid function. And the way you learn the W, so again, we are going through very basics, but it's important to understand how it's set up. So it translates to nonlinear and deep learning models as well. So how do we learn the W? For every data point xi, I want W transpose xi to be greater than 0 if y is plus 1, and I want it to be less than 0 if y is negative 1. Dots. What if I have a blue dot here? Is it linearly separable? No. But it's almost linearly separable because there's only one data point, one blue dot that's sitting on the other side. So for that one blue data point, you will not be able to do this, right? But for everything else, you'll be able to do it. So for linearly separable or almost linearly separable data, you can learn a W, and you learn it through optimizing a loss function. And what's the loss function for this, for learning logistic regression? Sorry?
Indirect classification.
Yeah, but what's the loss function? It has a name.
Roots.
It's not MSE. MSE is good for regression. This is a very popular interview question as well. So if you're doing any machine learning interviews, what's the loss function for logistic regression? It's cross entropy. So we'll look at that. So cross entropy is actually based on the probability of predicting a positive class or negative class. So it's based on that. So probability of a class in logistic regression, the score W transpose X is converted to a probability through a sigmoid function, right? So you can talk about probability of Y, the prediction equals +1 or prediction equals -1, right? Because you just change it, like you can just do it this way. So it's 1 over 1 plus e to the negative W transpose X times Y hat I, right? If Y hat I is -1, you get a probability for -1. And if Y hat I is +1, you get a probability for +1, right? So based on this probability, you can actually define a loss function. And let's look at the loss function. Yeah, it's here. So this is binary cross entropy, which looks like this. So you want Y hat I to be +1 when this is +1, and you want it to be -1. If this is -1, you want it to be -1 here, right? Or you can also use 0 and 1. I think here we're using 0 and 1. So let's look at this. So if Y hat I is 0 and Yi is plus, let's say it's 1, what is the value here? So you'll actually use this one, right? You'll actually get that the loss is 0. Loss is Yi is 0. Yeah, so yeah, you'll actually use this. So the loss will be negative, it'll be plus infinity. Yeah, because it'll be 1 minus 1, 1 minus, okay, Yi is 1. Okay, yeah, sorry, we'll be using this one. So Yi is 1, so we'll be looking Yi log Y hat I. So there's 1 times log 0, which is negative infinity. And we have a negative sign, so the loss is infinite if you get the prediction wrong, okay? But if you get the prediction right, what's the loss? So if the prediction is right, so that is Y hat I is 1 and Yi is 1, then we are looking at Yi log Y hat I, which is 1 log 1, which is 0. So you incur no loss if you get the prediction right. You incur infinite loss if you get it wrong, right? That's kind of how it is set up here. So typically your Y hat I will not be 0. It'll be somewhere between 0 and 1. So you'll not be hitting this infinite thing in training. So it'll be like 0.3 or 0.7 or 0.8. So you don't have to worry about infinite things happening in training. But the idea is that this loss function is the loss function because it promotes things that match up with the true label, and it really penalizes things that don't match up. And that's why it's called a loss function. You incur a lot of loss if you don't match up, right? Okay, let's do a simple in-class exercise before we go further. So we'll go into some of the details in this class so that you get a grip on it. So hopefully everyone has your canvas open. It's a very simple linear algebra question, really basic. So it's to compute W transpose X, if W is this and X is this. Just maybe take like 30 seconds to a minute, and then you can just plug in the option on canvas, and then we'll go to the next section. So we'll look at activations a little bit more. So there are many different activation functions, but there are a couple that are very popular. So sigmoid is still used, but mostly only at the output layer. And when it's used at the output layer, it becomes a softmax that converts the prediction into a probability. So if you have 2 classes, you get a probability over 2 classes. Otherwise, if you have n classes, you get a softmax, you get a probability over n classes. So sigmoid is these days typically only used in the output layer, because people have shown that if you use it at the hidden layers, in between layers, you don't get as good a performance. Then we also have the tan H. This is also like sigmoid, but it's more zero centered. Again, for the same reason, it's not, it used to be that people would use tan H or try tan H, but the more popular one is ReLU, so rectified linear unit. So rectified linear unit, it says that if you're negative, I'll just keep you at 0. If you're positive, I'll pass you through as is, right? So it's gating negative versions. But then people said, well, if it's negative, you're never passing it through, you're always zeroing it out. So can we soften that? So then we have versions like noisy ReLU or leaky ReLU. So let's see here, yeah. So this is ReLU, which is like completely flat. And then we have leaky ReLU that allows for some leakage of negative values. And then if it's positive, it just lets it through. So very simple variation of the linear function. So it's linear on the positive side, it's truncated or capped on the negative side. So a simple modification. Yeah, and it works. ReLU works pretty well. So sigmoid versus ReLU, I think we spoke about this. So sigmoid is used in the output and ReLU is used in the input. Overfitting. Okay, I'll draw 3 graphs and I want you guys to say which one is overfitting and which one's underfitting. Okay. So let's say we have data points like that. Actually, it has to be the same kind of data. Okay, so this is an example of linear regression or regression. You're regressing through points. So which one is overfitting and which one is not? Second one is overfitting. Yes, because it literally is that you're trying to fit through every single point and it works. It works only on this data set. If for some reason I use a different data set, let's say this line is going down this way, okay? What if on my test data set I had an X here, right? Then I would actually be way off on the prediction. Although on the training data, I'm perfect. There's 0 error. That's why it's an overfitting is an issue. Is like overfitting also, how do you identify overfitting on training? Sorry?
Degrees is too high.
What is too high?
The degree.
Degree is too high, yeah. But let's say based on training loss. Suppose you had to look at training loss.
So that would mean that your training set is good, but your test set is terrible.
Yeah, so you see a discrepancy between train and test. On train, sometimes you might even get 0 loss or close to 0 loss. And on test, there's a big gap. The loss is much higher. So then you know you're overfitting. So overfitting is just that, like you have some data, but the data is not complete or your model is too complex that if you overfit, you might actually be going off on other data that you have not seen. Unseen data you might be doing worse of. So it's overfitting is happened when your model complexity is higher than the data complexity. The data is not as complex, but you fit a much complicated model, and so that's when overfitting happens. Or overfitting also happens when the number of data points is less than the number of parameters of the model. That's another way of looking at it. You have too many parameters in the model and too few data points. That's when, like for example here, how many data points do we have? How many data points? 4, right? There are 4x. What is the, this is a, what is this? This is a polynomial, right? What do you think is the degree of this polynomial? Is it 1 degree, 2 degree? No. 3 degree? It's probably 4 degree or 5 degree or higher, right? So degree is greater than 5. So you can see that the complexity of the model is greater than the number of data points. So you're overfitting. So overfit complexity of model is greater than number of data points. And this can be measured by a number of parameters. Okay, and you can also have underfitting. Your data has a lot of complexity, but your model is too simple. Like I could have an example where, let's pick an example. So maybe your data looks like this. Right? There's some kind of a trajectory like this. Okay? But you decided to fit a linear model. So it's underwhelming to have a linear model for data that has a certain pattern. So this is underfitting. You're not fitting enough. You need to fit a more complex model because the data has more complexity to it. So that's the case of underfitting. Okay. All right. So any questions on overfitting, underfitting? All right, so we'll go through a small demo. So let's go through the TensorFlow demo here. It's pretty instructive. So yeah, I think, we have different kinds of data sets here. Is this data set linearly separable? Yes? Okay. So if I reduce the number of hidden layers, so we have 0 hidden layers, okay, and I can hit train here, and you see there are different activation functions, learning rate, regularization, which we didn't talk about, but let's ignore it for a bit, and you can choose a classification or regression type. So this is classification. So if I actually do training will just generate a bunch of data points, bunch of blues and bunch of oranges, and your data is in how many dimensions? 2 dimensions, right? So we are learning a weight vector that's in 2 dimensions. So your W is in 2 dimensions, okay? So you see that white line, that's the weight vector. Perpendicular to that is a weight vector that was just learned on this data that separates the blue from the orange. So straightforward, because the data is simple. So you don't need a complicated model. All right, so I mean, this keeps going, but we can just stop it here. Let's look at something more complex. Okay, XOR. This looks like XOR, yeah. So we looked at XOR, and so the orange is one class, and the blue is the other class. So let's train a simple model, and it's not really able to separate the orange from the blue. Okay. You can see the test loss and training loss are high. So we are in what scenario? Underfitting, overfitting? Underfitting, because the data is more complex than the model. So you can see the loss is also high, right? Going back, let's look at the loss here. You see the loss? it's gone practically to 0. But the test loss is also 0. So it's not like we're only having a train loss that's close to 0. It's also the test loss that's 0. So this is just right fit, right? Okay. Now let's go to XOR, and let's say I add more features. So we spoke about feature engineering, remember? This is an example of an engineered feature. X1, X2 was not part of the data. We only had X1 and X2, right? But if I can engineer a feature called X1, X2, I can just multiply an X1, X2. So that's an engineered feature. Once you engineer a feature, if it's meeting your requirement, even a linear model will work. So this is what people used to do before. So let's engineer this feature. Now if I train, look at that. There is perfect separation between the orange and blue. Even with a linear model, right? We don't have any hidden layers. So it's still a logistic regression model that's perfectly separating because we had an engineered feature called X1 and X2. If I remove this, it's not going to work anymore, right? Okay, so that's feature engineering. Let's look at the neural network way to actually separate. So we said that, I think if you remember right, we said one hidden layer with 2 neurons should be able to learn the XOR, right? So let's test that assumption. Okay, let's change the activation function here. We'll change the ReLU. Kind of getting there, but not really. Let me change the learning rate. 0.01 is too high, maybe. Yeah, okay. It should work, but maybe there's some optimization issues, so let's actually give it more neurons. Let's try that. Keep it here, okay. Okay. So in our theoretical example, 2 neurons in 1 hidden layer was sufficient, but practically, you know, there's some optimization issues or training issues. We added 2 more neurons, and now we have good separability between the classes.
In the example that you were showing, there were actually extra.
There was intercept. Oh yeah, there was intercept as well.
So you had the bias.
Right. We had the bias term. Okay, that's a good one. Yeah, that's a good one. Okay, so this is more complex. So either you engineer a feature, and these days people don't do feature engineering. So you have to depend on more neurons and more layers. Okay. Let's look at one more example, maybe this one. This is even more complicated because there's like a circle of points within a circle of points, right? It's like 2 rings. So in a Euclidean distance, blue might be close to orange, right? Like this point is close to this point in a Euclidean sense, but they belong to different classes. So that's the complication of this data. So let's try, I mean, we obviously know that a linear model will not work, so let's not try that. But let's try this model. Okay, so that worked. Let's try to reduce the number of neurons here. Let's try if that works. Oh, that works too. Okay. Let me try to reduce until it fails. I think it's failing here. You see the loss function is 0.256. Now let me add one more neuron. Yeah, loss function is 0.01 for both train and test. Okay, so just one additional neuron in the one hidden layer made a difference on learning this data. So obviously this is in 2 dimensions. The data is in 2 dimensions. So as you increase the number of dimensions of the data, things become more complex. And we can't even visualize parameters learned in higher dimensional space, right? But this is a good illustration in 2-dimensional space of how things get affected, right? Yeah. There's also this one, spiral. I'm not sure how many layers. I think this, yeah, this is another example, right? So here, I try this, doesn't work. My loss function is at 0.48. Let me try adding more neurons. Still doesn't work. So here the problem is I'm only having one hidden layer. So I need to go to a second or a third hidden layer. So the deeper the network, the more complexity it can handle. And you can see spiral is super complex because it's kind of like, things are very close to each other. So let's add one more layer. Let's see if this works. Okay. Let me add one more layer. Yeah. I think there's also probably a need for regularization. I'm not sure. Let's add one more and see if this works. Yeah. Let me add some regularization. L2.03. So this avoids overfitting as well. So we can. Wow. Okay. All right. You look at the loss function as well. Look at this graph as it's going down. It's going down for both test and train. So it's figured something out. It's not great, but it's working because the loss function is actually, so it's stalled here at 0.007. And in order not to overfit, I had to use this regularization. If I didn't use it, I think it didn't work as much. Or it did. Yeah, it gets a little bit weird. Okay, so this is an example where you had to have had 4 hidden layers for it to actually differentiate the spiral, right? So this is already a deep neural network where the data was sufficiently complex, even in 2 dimensions, that you really needed 4 hidden layers to be able to differentiate the blue from the orange. Okay. Any questions or thoughts? Yeah.
I think maybe it's obvious, but as you're going from left to right, you can see that it's able to represent more and more complex, feature mapping.
Yeah, with the neurons?
Yeah.
Yeah.
Like you see, it's just kind of like single lines, and that's because you're combining them together, right? So
Yep.
it's more and more complex.
Yes. That's a good observation. So this is like just the first layer. So it's essentially learning linear features, but then these are based off these, so they get more and more complex.
Is there like a rule to this of like complexity versus layers, I guess?
Yeah. I think this is true with vision as well. We'll see an example now where the initial layers are more primitive and then the later layers are more and more nuanced and complex.
It's kind of like the answer of like why deep learning works in a way.
Sorry?
That's kind of the answer of why deep learning works in a way.
Yes. It's kind of learning the basics or building blocks in the beginning and then combining them later. So it's kind of an analogy for that. Yeah. How does regularization? Okay, so regularization. So here we see like there's L1 and L2. Regularization is like a clamp on the weights. So it's shown that when things overfit, the weights kind of get bloated out of proportion. So it says let's clamp your influence. So by clamping the weight, you're clamping an influence of any single weight. So it's an additional term that's added to the loss function, and so it's like a L2 regularization is like the quadratic function on the weight vector. So it uniformly clamps the weights, and then L1 produces some sparsity as well. Some of them are 0, some of them are not. So it selects the weights. So it's also like I think in the earlier days we used to call this feature selection. So L1, L2 also support feature selection and help you pick which places to emphasize and which not to. So that's kind of the short answer. Okay, yeah, the link for this is in the lecture, so feel free to play around with it and the different data types that are mentioned here. And yeah. So that was a TensorFlow demo. So you can take a look at the link here. So yeah, I think this goes back to some question that someone asked. to understand a little bit better on how the layers of the deep learning model work, computer vision before deep learning works on understanding images and videos, was to first extract features that are hand curated or hand created, right? Like use of convolutions or whatever, and then use simple classifiers later. Like we saw an example with XOR. If you had x1, x2 as a feature, the linear model works on it because you have a x1, x2. That's a nonlinear feature, but a linear model. So at the end of the day, it's still nonlinear, but you handcrafted or engineered a nonlinear feature to and then use a simple classifier, right? So this was like the traditional method before deep learning came into vision, is people would spend a lot of time and write papers on handcrafted and hand engineered features that could be nonlinear or sophisticated, and then apply a simple classifier later. So after deep learning, people notice that you don't need to do it as much anymore because the layers start capturing the features or learn the features on their own. So if you had an image, then it could identify some edges or some colors in the initial features, and then it starts to have more patterns in the later features. You can see the patterns here. And then layer 3 also has some personas or more sophisticated features. So the complexity of features would grow from the initial layers to the final layers, and then you would have the prediction at the last layer. So simple to complex features learn. Right. Yeah. So another example here is like if you had an input, you first identify the edges, and then you identify combination of edges. Then you identify some more distinctive features like eyes or nose in an image, and then you can generate an output, right? So it's like a step-by-step process. So yeah, having more layers, each layer can, like people have done it, like you train a model and then you say, what does this layer do? What does this layer do? So you can actually pass an input through the layers and then examine what it looks like at the intermediate layers to understand what that layer does. So a lot of understanding deep learning is more of that. You train a model and then you ask this question, what does this layer do? So you take the image through the layers and then examine it at that intermediate layer to understand what it does. What's the function of that layer, right? So yeah, so that's like an example with computer vision. Okay. I'm sorry, this is a little bit of a tricky thing to work with. Okay, yeah. All right, so feed-forward deep learning architecture. So we have an input X. So this is actually in P dimensions. Then we have weight matrix. So instead of a weight vector like we saw with logistic regression, we are having a weight matrix between layers, right? And the weight matrix goes from the input dimension to the next dimension. So let's say this is in D dimensions. So W1 would be P by D, right? Because it takes a P dimensional input and then transforms it into a D dimensional output, right? And there'll be like activation functions at every single neuron. And you go through all the layers and then you get the output. And the output also is let's say it's a classification, it's like a probability distribution across classes. So if you had, for example, here we have like 10 classes, you'd have a probability distribution across 10 classes. Okay. So let's do a in-class exercise with understanding the number of parameters in a deep neural net. So consider a deep neural net model with 3 hidden layers, where each hidden layer has 1,000 neurons. And let the input layer be raw pixels from a 100 by 100 image, right? So you have image of dimension 100 by 100. and the output layer has 10 dimensions. And let's say this is for a 10 class image classification example, which makes sense, right? Because the output layer has 10 dimensions. So the question is, how many total parameters exist in the DNN model, right? Roughly.
And it's fully connected.
It's fully connected. So maybe just first set up the architecture. Okay, you have input, then you have hidden layer 2, hidden layer 3, and then you have the output.